Dr. Prashant Srivastav. He's a very renowned scientist and working at Adelaide University, Australia. And as per program, he will deliver the lecture on environmental implication on circular economy. Similarly, we have another very good scientist working in the field of this water related issues concerned with the environmental, and he will deliver his lecture on agriculture water sustainability, and he is from ICR Sifat Institute, Ludhiana. And another speaker, learned speaker, is Dr. Pankaj Srivastav. He is working on microplastic contamination. The microplastic contamination it is becoming a very big burning issue nowadays, and we cannot see from our open eyes that how much quantity of these plastic we are utilizing in our daily life. So Dr. Pankaj Srivastav, I think, will deliver that in his lecture. He will open our eyes that how problems we are facing, how much problem we are facing in our daily life through this microplastic problem. And one of another renowned scientist is Dr. Arjun Singh. He's our colleague and working in CSSRI, and he's having expertise in the field of agriculture plastic. That this how much quantity of this plastic is going to our soil, our plant system, our food chain, everything. He will, I think, he will cover in his deliberations. So from so friends, you know very well that the plastic use has become part of our daily life. If you see from kitchen to it plastic use, it reached to from our kitchen to our even our bedroom. Everywhere we are using the plastic. If you see even our kids going to school, going kids, they are using they started from very beginning, from the date of school going, they are using the tiffin. The tiffin is a lunch box that is also made of plastics, and even water bottles they are using. So how from the initial stage we are promoting that we are not we can't say that promoting, but we are using this plastic. It has become the part of our life. And you see the if you see the position of worldwide, what is the status of this plastic? The world is producing about 5.53 million metric ton of plastic waste every year. This is the data from the world producing 53 million metric ton plastic waste every year. And all out of that, only 9% of that the plastic which is being produced worldwide only recycled. Only 9%. And rest of the plastic is you can say is contaminating our environment, our oceans and our rivers, and in our is not you can say that is not recycled. And so it leaches with this plastic, it leaches toxic elements into the soil, ground, water, and pollute rivers, where the non-recycled plastic is going to the our soil, and they are polluting our soil, our groundwater, and even our rivers. And I will give you one example. If you read the newspaper during 2019, when a whale came on the sea coast, and when we found that in Philippines, we found that 40 kg plastic from the stomach of that whale. So this is the situation, how much our marine population, our animals, our marine system, our entire ecosystem is affected with this climatic environmental problem. And if you see the data of developed nations, and the developed nation, or they are how much quantity they are using the plastic in our daily use per person. If you see the US data, in US plastic consumption is 109 kg per year. 109 kg per year per person is using in United States. However, in India, its consumption or it is only less than 11 kg. And similarly, in case of in China 60 kg per person per year is using the plastic. So how much the situation is become deteriorated day by day. And because of this, there are certain problems we are facing. The plastic pollution has become a significant threat to our environment, affecting ecosystem, our wildlife, and human health. The widespread use of the plastic, particularly single-use plastic, has led to a massive accumulation of plastic waste in our ocean, our landfills, and our natural habitats. If you see the impact of plastic population, you will find that our marine life, like sea turtles, fish, and other animals, get entangled in plastic debris. Plastic pollution is linked to various health issues like cancer, reproductive problems, and respiratory diseases. If you see the respiratory data of India, respiratory diseases because of the environmental pollution, about 35 million people in India are suffering from asthma disease. If you see this is because of this environmental pollution, 35 million people are in India are suffering from asthma. Similarly, animals, they are affected with the reproductive cycle of animals, and their respiratory systems are severely affected with this environmental problem. Similarly, wildlife, if you see one example I will cite, earlier we were found that vultures in India, there were large quantity of vultures were available. When there were any animal dead, and vultures immediately came to that site, and they used that the flesh of that animal. So nowadays, if you find there is in India, there is no vulture. Vulture is not, they disappears permanently because of this environmental pollution. And similarly, the marine life, as I told you earlier. So the plastic pollution affects our ecosystem, leading to biodiversity loss and ecosystem disruption. There should be proper strategies. So what should we do? There should be proper strategies to combat the plastic pollution. If you see in India, the statistical data of India, India generated about 3.2 million ton this e-waste. There are many other environmental contributing factors are like e-waste, which contain जो इलेक्ट्रॉनिक वेस्ट लाइक हमारे घर से जो टीवी है और जो कंप्यूटर है, मोबाइल है, जो इनका जो निकलता है, दैट इज 3.2 मिलियन टन पर ईयर कंट्री से ये प्रोड्यूस हो रहा है, जो कि वो भी हमारे इन्वायरमेंट को विच कंटेन हार्मफुल सब्सटेंसेस दैट कैन हार्म टू पीपल एंड इन्वायरमेंट. And then another contributing factor is, if you see the construction waste in cities, in mega cities, or you can see the metro cities, everywhere there is a construction is there. So the construction waste which is generating, which is also creating the environmental problem. According to the International Union for Conservation of Nature, in India, around 97 mammals, 94 bird species, and 482 planet species are at risk of extinction because of this environmental pollution. 97 the animals, mammals, and birds, and the plant species, they are in the extinction stage. And between 1972 and 2018, population of wildlife animals fell by 69%. This is, you can see the situation, what we are facing, what our ecosystem is facing because of this environmental pollution. And 69% wildlife animals की population कम हो गया है because of this environmental problem. And you see the India is generating 9.3 million ton plastic waste annually. The Indian situation, if you see, 9.3 million ton plastic is waste is generated annually. And then out of that, 26,000 ton plastic waste every day. If you calculate it, it is 26,000 ton plastic waste is generated every day in India. Only 8% of that production is recycled in India. Only recycled is 8%, and remaining 92% is in you will find everywhere in rivers and nalis and our soil, and where. So India has become the world largest contributor of plastic pollution. So this is the situation now we are facing. So at the end, I would like to say that to combat the plastic pollution, a collective efforts from the individuals and from communities and from organization and government So we should work in a combined approach to combat this plastic problem, environmental pollution. So with these remarks, I would like to thanks to the organizer once again, and I would like to thanks to our learned speakers who spared their valuable time to participate in this webinar. So thank you very much once again. Thanks to all.
Thank you, Dr. Singh, for opening remarks. Now I request Dr. Vivek Arya, who is organizing secretary of today's webinar, to introduce the speakers. Dr. Arya?
Yes, sir. Am I audible, sir?
Yes, yes, please.
First of all, I would like to thank the ANRCM for providing this opportunity. And I am also thankful to the core committee that from time to time, in a very short span of time, they had organized various programs on various themes. And they had tried to collect the scientific community from the different spectrum. So by going on this particular thing, it was pre-decided that we will be trying to inculcate the scientific fraternity from across the globe having the expertise. We are very lucky and we are very thankful to all the experts that on the request of Dr. Sanjay Arora and Dr. A.K. Singh, they had accepted the invitation. Dr. Prashant Srivastav, sir, is a soil contaminant chemist at CSIRO Australia's National Science Agency based in Adelaide, South Australia. He earned a master and PhD in soil science from GB Pant University of Agriculture and Technology and another PhD in environmental soil chemistry from University of Sydney. With 30 years of vast experience, his research covers environmental contaminants, waste management, recycling, and the circular economy conducted across India, Japan, Australia, and the USA. Leading multidisciplinary research team, Dr. Srivastava focuses on assessing, remediating, and managing environmental contaminants. His collaborative work has significantly improved contaminated site assessment in Australia and internationally. His current research focuses on emerging contaminants like PFAS, microplastics, which the earlier speaker, our senior vice president, was referring that it had reached to the brain, lungs, and heart of our human life, tire rubber chemicals, e-waste, and radionuclide in soil water, biosolids, and pavement material, and the beneficial reuse of brine from coal seam gas mining. Dr. Prashant Srivastava, sir, very young scholars, PhD, MSc from across the country, they have joined this today's webinar, and it will be an honor for them to listen to you. The mic is yours, the dice is yours, sir. Thank you.
Thank you very much. Please give me 2 seconds to share my screen. Can you see my screen now?
Oh, good God.
Yes?
Very
Yes, we can see the screen.
Okay.
Yes, yes,
was a thought.
it is visible.
Okay. Thank you.
Audience,
So-
please mute your mic. Audience, please do not disturb during the presentation. Please, sir.
Okay, good morning, everyone. At the very outset, I would like to thank the Academy, particularly Dr. Arora, Dr. YP Singh, and Dr. Kohli for inviting me to this event on the occasion of World Environment Day. I'm absolutely delighted to be part of this August gathering. Given the theme of this mini conference today is plastic pollution, I'll talk about the environmental risks and implications of circular economy with a particular focus on plastics and microplastics. So before we talk about circular economy, let's go back in time and see how plastics became such a big part of our lives, and how something once seen as a modern miracle has now become a serious global problem. Synthetic polymers first appeared in the late 19th century, around the 1860s. But it wasn't until after World War II that the plastic boom really took off. It all began in 1907 when a Belgian-American chemist named Leo Baekeland invented Bakelite, which was the first completely synthetic plastic. This invention was a major turning point in human history because for the first time we had a material that did not rely on nature. It could be molded into any shape, it was durable, it was cheap to produce. From there, the plastic revolution took off. But why did plastics become so popular? Well, because they ticked all the boxes. They are lightweight, so they are very easy to transport. They are resistant to corrosion, which means they don't rust or decay. They are waterproof, they are airtight, and they insulate heat and electricity. And most importantly, they are cheap to make. So in short, plastic was the perfect material for modern living, or so we thought. But here's where the story takes a turn. Because plastics are so durable, they don't break down easily in nature. Instead of decomposing like organic waste, they stick around for hundreds of years. Over time, the plastic we throw away builds up in landfills, rivers, oceans, and even the air. And it doesn't stop there. In the environment, plastic items slowly break down due to sunlight, waves, and friction, and turn into tiny pieces called microplastics. They are now found everywhere in the ocean, fish, in drinking water, in soil, and even inside the human body. So, what started as a modern marvel is now seen as one of the world's most pressing environmental threats. It's a global issue and it affects wildlife, ecosystems, and even human health. So, as we move forward, it's important to remember plastics aren't all bad. They have helped improve lives in many ways, but the way we produce, use, and dispose of plastic needs to change if we want a cleaner and healthier future. So, understanding the scale of the problem is the first step towards solving it. Now, let's look at just how big the plastic problem really is. Dr. Y.K. Singh provided a broad overview, but I'm just going to present some data from the recent literature. So imagine plastic like a stream that began in the 1950s. But over time, that stream has turned into a flood. In the last 75 years, since 1950, the world has produced over 9.2 billion tons of plastic. And if we don't change the course, this could rise to more than 34 billion tons by 2050. In just 1 year, 2022, the world produced over 400 million tons of plastic. And that's a 200-fold increase from just 2 million tons in 1950. And most of this plastic, around 91% of it, is still made using fossil fuels. Now, what happens to all this plastic after we use it? Between 1950 and 2017, about 76% or 5.3 billion tons was simply discarded, often into landfills or the environment. Only 14% was burned, and just 8%, around 700 million tons, was recycled. Around 2.9 billion tons are still in use today. So the result? An enormous and growing pile of plastic waste on our planet. This is especially important for countries like India, where plastic use is expected to grow the fastest over the coming decades. If things continue as they are, plastic waste in India could double by 2040, reaching 4.1 million tons of plastic waste every year. And much of it will end up in our rivers and oceans. Globally, plastic pollution is projected to grow by 70% by 2040, especially due to short-lived items like packaging. And unless we change the course, the plastic leakage into nature could reach 30 million tons every year. And if you look at who's producing all this plastic, in 2022, China led with 32% of global production, followed by the rest of Asia at 19%, Europe at 17%, and North America at 14%. And most of this plastic is used in packaging, consumer goods, and construction. While plastic is convenient and lightweight, it's mostly designed to be used once and thrown away, not reused or recycled. And that's why we need to move towards a circular economy, where plastic is reused, recycled, or replaced with sustainable materials. I'll talk about that in a few minutes, but the system we have today simply cannot continue. So let's talk about something which is really tiny, but has a huge impact. It's called microplastics. I'm sure you've heard the term before, but what does it really mean? Now imagine a plastic bottle floating in a river or the sea. Over time, sunlight, waves, and friction break it down into tiny fragments, just like a biscuit breaking into crumbs. These fragments are called microplastics. The term microplastics was first used about 20 years ago when scientists noticed small bits of plastics in seawater, marine sediments, and at various other places. Today, microplastics are usually defined as plastic particles smaller than 5 millimeters, about the size of a grain of rice or even smaller. They can be either primary microplastics, which are made small on purpose, like microbeads in some personal care products, or tiny fibers which are shed from synthetic clothing during washing. Then we have secondary microplastics, which are created when larger plastics like bags, wrappers, or bottles break down slowly in the environment due to sunlight, waves, and abrasion. But where do most of these microplastics come from? On the bottom right, you can see some of the main sources and their estimated contributions to global microplastic pollution. Synthetic clothing fibers. About 30% of microplastics in the ocean come from clothes made of polyester, nylon, and synthetic fabrics. Tire wear. As tires rub against roads, tiny particles are released, making up roughly 28% of the total. City dust and road wear, around 24% comes from weathered surfaces, construction materials, and everyday wear and tear. So the clothes we wear, the roads we drive on, and the products we use every day are all part of the microplastics story. These tiny particles are now found in oceans, rivers, soils, and even in the air. When we think of plastic, we usually imagine a single material, like a drink bottle or a food wrapper. But plastics are not simple. They are made from polymers, which are usually derived from fossil fuels, and which are mixed with thousands of chemical additives that give them different properties. For example, flexibility, durability, color, or resistance to heat and sunlight. Some of the most common additives are plasticizers like phthalates, which make plastics soft and bendy, flame retardants, which slow down burning in items like electronics, stabilizers and antioxidants, which help plastics last longer, bisphenols like BPA, which are found in clear plastic bottles and food containers, PFAS, which are found in the products which are claimed as a non-stick or stain resistant or waterproof, heavy metals and pigments, which are used in color plastics and toys. So while these chemicals serve functional purposes, many of them are not tightly bound to the plastic. That means over time, especially when exposed to sunlight, heat, or wear, they can leach out into the environment and into our bodies. And it doesn't stop there. As plastics break down into microplastics and nanoplastics, they don't just get smaller. They carry these chemicals with them, entering the air, soil, water, and food chain. But why is this a concern? More than 3,200 plastic associated chemicals are classified as potentially hazardous. These chemicals can be released throughout plastic's life cycle, from manufacturing to everyday use, and especially during disposal. For example, when plastic waste is openly burned, it releases toxic compounds like dioxins. We are exposed to them in many ways. For example, by breathing contaminated air and indoor dust, by eating or drinking contaminated food and water, through skin contact with plastic products like packaging, toys, and textiles. People working in plastic and waste industries face especially high exposures. And children are particularly vulnerable due to their size and developing bodies. Scientific evidence links these exposures to reproductive disorders, hormonal disruptions, neurological impacts, and even increased cancer risk. Even the tiniest plastics found in the placenta, breast milk, and lungs may cause physical damage, inflammation, and long-term health effects. This makes plastic pollution not just an issue of waste, but also a global chemical and public health challenge, something that requires urgent attention to reduce harmful chemicals and protect human health. So, how do we fix this problem of plastic pollution? The answer lies in moving away from the old take, make, dispose system, where plastic is used once and thrown away, and shifting towards what is called a circular economy. That means designing plastics to be reused, recycled, or safely composted, keeping them in use for as long as possible. This shift could not only stop plastic pollution, but also save trillions of dollars in environmental and health costs. So here is how we can get there. To break this cycle, we need action on multiple fronts. Number one, stop plastic at the source. What this means is reducing the production of unnecessary plastic, such as excessive packaging and single-use items that are used briefly, but they last for centuries. Number two, make plastic safer. As mentioned in the previous slide, plastics often contain hazardous chemicals. We need to phase them out and replace them with safer, more sustainable alternatives that don't contaminate recycled materials or the environment. Number three, improve collection and recycling. Robust systems for sorting, recycling, and managing plastic wastes are essential. Number four, strengthen policy, science, and transparency. We need clearer regulations, more investment in research, and tools like digital product passports to track plastic content and recyclability. Everyone, from manufacturers to consumers, must have access to this information to make informed choices. Number 5, raise awareness. Clear labeling, public education, and behavioral change are the key to helping people reduce, reuse, and recycle more effectively. But these solutions are not going to work in isolation, as Dr. YP Singh mentioned in his lecture. What we need is a fundamental shift in the way we design, use, and recover plastics, a system that keeps material in use and out of the environment. And this now brings us to the concept of circular economy, a smarter, more sustainable way forward. And that's what we will explore. We'll explore in the next slide. So far, we have seen how plastics, especially microplastics, are everywhere in our oceans, in our soils, and even in our bodies. And it's largely because of the way we currently use materials, a system called the linear economy. We take resources, we make products, use them, and then throw them away. It's a straight line, take, make, dispose. This model has led to serious challenges, especially with plastics. We are extracting more fossil fuels than ever to make new plastic. And we are generating massive waste that does not break down, and it contributes to plastic and climate change. And that's where the circular economy comes in, which is especially relevant for tackling plastic pollution. In a circular economy, we redesign plastic products and packaging such that they can be reused, repaired, recycled, and as long as it's possible. Instead of plastics ending up in the landfill or the environment, they stay in the system, looping back through multiple lives. And this means phasing out unnecessary and single-use plastic, using safe, non-toxic materials that can be recycled back without risk. Designing products for durability and recyclability from the start, and investing in better collection and recycling system, so we can recover plastic instead of wasting it. When implemented correctly, this approach reduces waste, it conserves resources, and it limits harmful emissions. It also opens up new economic opportunities. It encourages innovation and helps protect both ecosystems and human health. So instead of seeing plastic as disposable, the circular economy helps us see it as a resource to be valued, safely reused, and continuously recycled, not discarded. So as we learned in the previous slides, recycling is one of the best ways to deal with plastic waste. It is important for creating a more sustainable circular economy, but recycling isn't perfect. And there are some serious problems that we need to be aware of. And one big issue is chemical contamination. Plastics are made with thousands of chemicals, including things like flame retardants and heavy metals. When plastic is recycled, these harmful chemicals can end up in new products like toys or food packaging, which can be dangerous. Another problem that we often don't know is that chemicals are in what chemicals are in a plastic product. Most plastics don't come with a label listing their ingredients. So it's hard, especially for small or informal recyclers, to tell which ones are safe to recycle. Without proper labels or tracking, harmful chemicals can easily sneak into new recycled items without anyone realizing. Also, plastics get weaker every time they are recycled. To fix that, manufacturers often add more chemicals, including some that haven't been fully studied. And these are called non-intentionally added substances, or NIAS. And we don't always know how safe they are. Some people think chemical recycling, where plastic is broken down into its basic parts, is the answer. But this method can also release toxic gases like volatile organic compounds and harmful compounds like PAHs, or polycyclic aromatic hydrocarbons, and it may create hazardous waste. In fact, some methods like turning plastic into fuel don't even count as real recycling under international rules. So what does this mean? It means recycling isn't a simple one-size-fits-all solution. We need strong rules, more information about chemicals, and better systems to keep toxic stuff out of recycled products. Recycling needs to be done smartly and safely, not just a quick fix that might cause other problems. I'll talk about some case studies on recycling of plastic products we use every day. I'll start with recycled plastic bottles. You know, the ones for water, soft drink, and juice. Most of these bottles are made from a plastic called PET, which is short for polyethylene terephthalate. So PET is popular because it's lightweight, it's strong, and best of all, it's recyclable. Sounds great? Yes. Well, here's where things get a bit tricky. When we recycle PET bottles, they often come from all kinds of places, different brands, different uses, different chemicals. And here's the problem. Some of these bottles may still have leftover stuff in them, like cleaning agents, color dyes, or other chemicals that were never meant to touch food. Now imagine this. Those chemicals don't just disappear. They can stay in the plastic even after it's been recycled. So if that recycled plastic is used to make a new bottle, one that holds your drink, some of those leftover chemicals might leach into the liquid. Not good. That creates potential health risks, especially if the recycled PET didn't go through proper testing. And because the plastic often comes from so many sources, it's hard to control the quality. Even with recycling, we can't always guarantee it's safe to use again, especially for things we eat or drink from. And that's why there are strict rules in many countries about which plastics can be reused for food packaging. But, and it's a big but, those rules aren't always followed everywhere. So what does this tell us? Recycling PET bottles helps the environment, for sure, but it also brings new challenges. It's not just about reusing materials, it's about making sure these materials are safe. Let's look at something else we use all the time: plastic bags and soft packaging. You'll see them everywhere in snack wrappers, frozen food packs, and even your shopping bags. A lot of these are made from recycled plastics. And that's a good thing, right? It helps reduce waste and cuts down on making new plastic. So far, so good. But just like with recycled bottles, there is a hidden side we don't always see. These recycled plastics can sometimes contain harmful chemicals like phthalates and bisphenols, and they are called endocrine disruptors, which basically means they mess with our hormones. Now, hormones control really important stuff like how we grow, how we develop, and how our ability and even our ability to reproduce. So if something interferes with that system, it can lead to serious health problems. These chemicals, again, can come from two places. Either they were in the original plastic or they got in during the recycling process. And because flexible packaging is often made from a mix of plastics, it's really hard to get rid of these dangerous chemicals completely. If that plastic is then used to wrap food, those chemicals can leach into what we eat. Think about that. A bag that looks safe could be hiding chemicals that you definitely don't want near your food. And that's a big worry, especially because this kind of packaging is used so widely in the food industry. But here is the tricky part. You can't tell just by looking. The plastic looks the same, whether it's clean and safe or contaminated with harmful substances. So again, recycling plastics like bags and wrappers helps the environment, but it's not always a simple process. We have got to manage recycled plastics carefully, especially when they're used for with food. And speaking of food, let's talk about something you might have seen a lot, especially if you have ever ordered food in a big city in India, let's say via um, Swiggy and Zomato. Black plastic containers. They look sleek, they are strong, and they handle heat well. But here's what most people don't know. They are often made from recycled plastic. And it's not just any plastic. Sometimes it comes from industrial or even e-waste. That means they can contain harmful chemicals like heavy metals or flame retardants. When you keep uh, them hot, or when you keep hot or oily food in them, those chemicals can leach into your food. But then there is also a recycling issue. Black plastic contains carbon black pigment, which makes it invisible to recycling machines. So it often ends up in landfills or is burned, adding to pollution and climate change. India already produces millions and millions of tons of plastic waste, and black containers just make it worse. So what's the point? Recycling sounds good, but if it's not done carefully, it can harm health and the environment. We need safer materials like biodegradable packaging or reusable containers, because true sustainability means thinking about what we use, how we recycle, and how it affects people and the planet. Now let's switch gear a little and talk about tires. You must have heard in the news that some roads are made from rubber or plastic. So here's a case study in which I conducted some lab experiment to test two types of pavement products made with recycled tire rubber. One was rubberized asphalt, and the other was a special pavement mix. These products include small crumbs or fragments of old tires, which might seem like a great way to reuse tire waste, but we wanted to find out, do they leak any harmful chemicals when they get in contact with water? And if so, could these chemicals be bad for fish and other aquatic life? So we collected two kinds of samples that use recycled tire rubber. The first was, as I said, rubberized asphalt, the kind used on roads, which contains about 3 to 5% recycled tire rubber. The second was a special pavement mix, which can contain anywhere from 30 to 70% tire crumbs and fragments, depending on how flexible they want the final product to be. For both types, we collected actual core samples, as you can see on the right. We also collected the samples of raw materials used to make these products to characterize the chemicals in these materials. Basically, we wanted to understand what's in these materials and what could potentially leach into the environment. Then we ran 2 different types of leaching tests to see what chemicals might come out of these rubber materials when they are exposed to water. The first test was meant to mimic what might happen if the material ends up in a landfill. It's a pretty tough test. We mixed the crumb rubber with water and we shook it for around 20 hours. And then we separated the water from the solids and tested the water to see what chemicals had leached out. Because it's so intense, we treat this as a worst case scenario. The second test was a bit gentler and more realistic. It's designed to represent what might happen in the real world when a road or pavement surface gets wet from rain. In this test, we placed one flat side of the sample in contact with water, as you can see in this figure, and left it for different lengths of time, anywhere from 2 hours up to 14 days. After each time period, we collected the water sample to see what chemicals had leached out and then replaced it with fresh water to continue the test. This whole experiment lasted about a month, as it's a shorter version of a method called US EPA's LEAF method, or Leaching Environmental Assessment Framework. Together, these 2 tests helped us understand how much and how quickly chemicals might be released from these recycled materials. This slide just shows all the different groups of chemicals we looked for in our tests. It's a long list because tires and rubber products can contain or break down into lots of chemical substances. We tested for things like metals, phthalates, phenols, hydrocarbons, tire-related chemicals like diphenylguanidine, DPG, or HMM, which help tires last longer. We also looked for a chemical called 6-PPD, which is a chemical added to tires to stop them from breaking down. But what's really interesting is that when 6-PPD reacts with ozone in the air, it turns into 6-PPD quinone. And that byproduct, 6-PPD quinone, has been linked to fish mortality in some places. So even though it's not added directly, it is something we still need to keep an eye on. So in short, this slide gives you a sense of just how many different chemicals might leach out of recycled tire and why it is important to study them closely. So let's now turn to what our leaching studies revealed about the potential environmental risks of these products made from recycled tire rubber. So in the case of rubberized asphalt, we observed that we observed leaching of aluminium and iron in the worst case scenario, with aluminium concentrations exceeding the Australian guideline values for the protection of aquatic ecosystems. In the more realistic test, which is the 1D leaching test, copper and zinc concentrations also exceeded these guidelines values. And we also detected 6-PPD quinone. Although only a small fraction leached, its presence is noteworthy due to its known toxicity to aquatic species, particularly fish. But the risk it poses under the field conditions remains uncertain at this stage. Now, turning to the proprietary product, we found that it had elevated levels of zinc in the worst case scenario, and again, copper and zinc exceeded the guideline levels in the more realistic test. We also observed hydrocarbons and a suite of tire rubber chemicals like DPG, HMM, and 6-PPD quinone in both tests, although no guidelines exist for some of these compounds. Now, it's important to understand that exceeding a guideline value does not necessarily indicate harm to aquatic system, but it signals the need for a management response. that these default guideline values are designed to be protective and precautionary, prompting further investigation rather than assuming harm. So while our study indicated the potential for some rubber-derived chemicals to pose risk to aquatic organisms, we need more research to assess the actual harm to sensitive receptors under the real-world scenarios. This study also highlights the importance of understanding the chemical leaching profiles of recycled materials and ensuring that appropriate risk management frameworks are in place. And so finally, what we have learned today. So as we have seen throughout this presentation, plastic pollution is not just a waste problem. It's a complex and multifaceted problem, from macroplastics to microplastics, from oceans to human bodies. Plastics and the thousands of chemicals they contain are now part of our global ecosystems. These chemicals, especially phthalates, bisphenols, PFAS, and 6-ppdquinone, are often unbound and can leach into air, water, soil, and ultimately our food chains. And this happens not just at the end of the life, but across the entire plastic life cycle. The circular economy offers a compelling and necessary solution. It encourages us to rethink how we design, use, and recover plastic materials, extending product life, avoiding unnecessary production, and minimizing waste. It's our best chance to reduce the flow of plastics into the environment while supporting economic resilience and innovation. But we must also exercise caution. As highlighted by the recent studies, including leaching tests from rubberized asphalt and proprietary pavement products, recycling can reintroduce hazardous substances, including heavy metals and toxic additives, into new products. So without careful regulation and transparency, we risk unintended exposure that undermine the very goal of circularity. And that's why clear policy guidance is essential, especially stronger legal frameworks and international coordination to manage hazardous chemicals in plastics. And looking ahead, we must invest in transparency, science-based thresholds, and better product design. And by doing so, we can ensure that circular solutions are not only sustainable, but also protective of environmental and human health. With that, I would like to thank you for your kind attention. I welcome any questions that you may have, and I look forward to our discussion on how we can collectively address this emerging challenge of plastic pollution while advancing the circular economy. Thank you very much.
Thank you, Dr. Prashant. It was very informative and useful presentation you made. I am thankful to you on behalf of ANRCM that you have accepted our invitation to be the part of this event. I request Dr. Vivek to take this program further and thank the speaker. And if any query from the participants can be taken by the organizing secretary, please. Dr. Vivek.
May I have some discussion?
Yes, Dr.
Yes.
Arjun.
Sir, very nicely presented, sir, and just a few queries on the estimation of PFAS from the soil.
Sure.
So right now, like we can do it by GCMS, but the extraction is the problem for the PFAS. Can you suggest some good papers on that so that we can optimize it in our Indian context? Because most of the work, like Australia is leading in PFAS, I know that, but India still the research on PFAS and BPA is still lacking. So if you can just provide us few references that from where we can just take up some methodology and we can optimize in our conditions and we can start doing it in our in our conditions
Sure.
also.
You can read my paper in 2022. So you just check my Google Scholar profile, and you can find a paper published in 2022, and there was one published in 2024 as well. But if you want to analyze PFAS in soil, I think the best way is to refer to the US EPA method, especially a method called method 1633. So that is especially for soil and water. And in simple terms, if you want to extract PFAS from soil samples, you just simply spike it with an internal standard, which is an isotopically labeled PFAS. And then you add alkaline methanol to it, shake it, and then decant it. Repeat that, a couple of times, and then you will have a, extract, which is like 15 mils or 20 mil. And then you have to evaporate it to reduce the volume to about half mil.
So
And then
the detection is only possible through GCMS, sir?
No. So it depends on which PFAS you're looking at. Most of the PFAS
Okay.
analysis is conducted using LCMS,
Yes.
triple quad LCMS. And the most important thing in PFAS analysis is the use of internal standards. So make sure you always use internal standard. I mean, we can talk about it offline. So because today's talk is on plastics, I don't want to bore people with PFAS.
I want to
So
Okay, thank you.
please email
This-
me, and I'll
Definitely,
send
sir.
you the
Definitely,
details.
I will
Thank you.
text you back.
Sir, there is one query from Dr. V.N. Sharda, sir. Sharda, sir, is one of the lead speaker. I think he had raised a query.
Yeah,
Yeah,
thank
please,
you.
sir.
A nice presentation, Dr. Prashant. And I want to ask one thing. How the temperature affects this microplastic release into the environment?
So I haven't done any work on effect of temperature per se, but my assumption is that it would release more chemicals from microplastics into the water.
Okay.
But as far as the release of microplastics, I mean, like the formation of microplastics is concerned, again, I think it would lead to greater formation of microplastics because the temperature will break down.
Why I ask this question is there's a lot of plastic litter lying here and there in the country, and I was just wanted to know how temperatures can normally earlier we were saying that okay, it takes 400 or 500 years for the plastic to degrade, but now with the knowledge of microplastic and nanoplastics, it is now being said that okay, once they are thrown into the environment, they start releasing microplastics or something like that. How true is it?
Yeah. So what happens is when the plastic is open in the in the open environment, and it's and the sunlight or the sun rays attack it. So the UV in the sunlight is actually impacting the plastic composition, and it kind of starts to disintegrate, and slowly and gradually it actually breaks down into small pieces. And even without the sunlight, it happens in our day-to-day lives. So if you go in your home, and if you have a plastic bag in which you put, let's say, a sari or a piece of cloth, and you put it in your Godrej Almari, and then next year when you take it out, you will see that that plastic bag has now crumbled into small pieces,
Yeah.
right? That's microplastics, and that's how it happens. So over time, what also happens is it starts to release the chemicals which were used as an additive in making the plastic, or the recycled plastic. And as and when those chemicals are released, it also kind of disturbs the overall structure of plastic, and And that's how plastic starts to disintegrate. And that disintegration leads to smaller and smaller particles, and which are then called microplastics.
Thank you.
Thank you.
Thank you, sir. And on the behalf of the ANRCM, I would like to extend our best wishes to you. And you have elaborated on a very important topic. And when we circulated this flyer, few of your friends from the GB Panth, they were very excited, and they have also joined because some of them are working with us, and many young scholars from across the spectrum, from Northeast, Central University, Imphal to Gandhinagar to Jammu Kashmir, they have joined. And definitely we will be sharing your email and along with your Google Scholar, so that they can be in touch with you if their work of expertise in future will be like that. So on the behalf, you have elaborated it in a very fine way, and I would like to urge the readers to read today's New York Times. They have a very good article, and even for those Hindi readers, there is one article in Amar Ujala written by Padma Vibhushan Dr. Anil Joshi from Uttarakhand, and he has written also very beautifully on today's theme. So with this, sir, on the behalf of Dr. Sanjay Arora, sir, VK Singh, sir, and Academy, we are highly thankful to you, and we look forward to work with you in future also. Uh, and wish you all the best in your endeavor, sir. Thank you very much, sir.
Thank you very much. It has
Dr.
been absolute
Prashant,
pleasure being part of this. And
Dr.
I'll be
Prashant,
very
we
happy
also,
to
yes, please.
I'll be very happy to be in touch with all of you. I often host the students and scientists from India to my lab, and if anybody wants to work with me here, you're always more than welcome. And I am always open to international collaborations, especially with India. Pantnagar being my alma mater, I always have a soft corner for people from Pantnagar. And I was actually a bit disappointed when I saw Dr. Thavamani couldn't join this conference, because Dr. Thavamani used to work with me before. Now he's at University of Newcastle. So anyway, thank you so much
Dr.
once again.
Prashant, we would also request you to join our academy. Dr.
Yes.
Professor Vara Prasad, soil scientist from USA, is also one of our member. And whenever you visit to India, then we organize some series of lectures across the country. We have different active members in many of the universities and institutes. That will be very useful for us. And thank you for sparing your valuable time, sir. Thank you.
Absolutely, my pleasure. Thank you very much again.
If you allow, I may like to.
Yes, Dr. Kohli.
And then I would just like to thank Prashant sir for accepting our invitation. And in fact, the title that you have chosen about this recycling or this circular economy, actually this has given us a very good take-home message, because whenever we talk of recycling, we seem to appear that we are eco-friendly. But then we should always remember that if you recycle each and every component throughout its life cycle, I mean, the very components, the very constituents of the recycling material should be kept recycling. At no stage they should be leaked into the environment, because you never know when it might be harmful. And you see, working in Australia, you have been able to document all these things, and especially in the third world countries, and even in India or even in other developed countries where these studies are not there, we are not even aware about this. Once we recycle something, we keep on appreciating ourselves and think that everything is done. Similarly, you see, if in case of fly ash also, it is being used to make roads, but nobody knows that the heavy metals in the fly ash are finding way to the aquatic ecosystem or even to the terrestrial ecosystems.
Right.
So I think this is a very pertinent question that you have raised and highlighted in today's speech. And all of us must keep this in mind and take this as a take-home message.
Yes.
Thank you very much, sir.
Thank you.
So, with the permission of Dr. Sanjay Arora, sir, can we proceed?
Yes, please proceed.
Yes, thank you. Then again, thank you, Dr. Srivastava, sir. And now our second speaker is Dr. Rakesh Harda, sir. He is an elder and a guiding force from PAU, and we all are very lucky that we have seen his work on Center for Excellence on Plastic. Dr. Rakesh Sharda is presently project coordinator of All India Coordinated Research Project on Plastic Engineering in Agriculture Structure and Environment Management. Dr. Sharda is former head of the Department of Soil and Water Engineering at prestigious Punjab Agriculture University, Ludhiana, from 23 to 23. In 2023, Dr. Sharda did an assignment at FAO as an international soilless and protected cultivation expert. He is the Chancellor nominee at Punjab University, Chandigarh. Dr. Sharda is in the Research Advisory Council member of many institutes like National Innovation Foundation, Ahmedabad. Dr. Sharda is a fellow of various professional societies. He started his professional journey from PAU Ludhiana in '96. He has been actively involved in research, extension, and teaching activities. Dr. Sharda has completed 22 extramural research projects from various agencies like DBT, DST, NABARD, ICR, amounting to almost 4,633 lakh, a huge amount in fact. He has received funding from DST, from IRI Philippines, from NFL, and he has vast 29 years of experience and had developed 28 technologies which has been inculcated into the package of practices of Punjab Agriculture University. We are very lucky that on the behalf of Academy, when Dr. Sanjay Arora sir and we contacted him, and he accepted our benevolent request, I will say, and he is with us. His publication is on the Google Scholar, more than 80 research publications in high reputed journals, and he has guided many students, and most of them, they are working abroad or in the country at prestigious universities at prestigious positions. And if you have the opportunity, to the young scholars, I would urge that if you have the opportunity to visit PAU, definitely go to the Center for Excellence, and you will see that what kind of wonderful work Dr. Sharda and his team they had done. So the dice is yours, sir.
Thank you,
And
Ji.
thank you.
Thank you, Vivek, for the nice introduction. But then they're just small workers doing the work only in the field. Of course, we are learners and we keep on learning. Share my presentation, just a second. So it is visible to everyone, I think so.
Yes,
Yes,
sir.
sir.
Yes.
Yes, sir.
Thank you. So my today's first of all, I wish that we celebrate this World Earth Day every year like this, and of course we live in unison with the earth. और जिसे we also say पर्यावरण पूरक जीवन वो होना चाहिए. And of course agriculture, water sustainability amidst climate change, exploring innovative practices. That is my today's lecture. And of course we all know that water is the most abundant molecule in cells, accounting for 70% or more of total cell mass. And of course, water is life. You can see how the water moves, and we also made up of water only. And if we go by surface water scarcity from between 1950 to 2024 in India, it is per capita availability from 5,200 liters. It will be going down to around 1,191 liters in 2024. And this also shows the per capita availability between the 2025 and 2050. You can see particularly in this area, it is the absolute scarcity less than 500 meter cube. Then and in some area it is no stress, but most of it is stressed. And if we go by groundwater used for agriculture in India is around 213 0.19 BCM. And of course, almost 95% of this is used for agriculture, 208.49 BCM. If we talk of Punjab, it's a deficit scenario that the requirement is around 66, total water demand is around 66.12 BCM, and agriculture water demand is 95%. That is at a high of 62.52. 62.52 BCM. And of course, the deficit is around 13.27 BCM. And this all is extracted from the ground only. And then we are able to meet our water requirement. And just by increasing the efficiency, that is where the point lies. Just by increasing the efficiency by 10%, we become water surplus. That is how the things are going on. And of course, this is true for any third world country. And enforcing and agencies are like not able to do so because of some political scenarios. But then, of course, if we adopt the if we are able to increase the water use efficiency by 10%, even in Punjab. So the challenges are food security, climate change, floods and droughts, urbanization, and conflicts. We all know that in 1947, the population was around 50 crores. It has swelled 3 times to around 150 crores. The climate is behaving very differently, even during this Rohini Nakshatra, which we call Nautapa, or the day with the highest temperatures. We are now having almost 5 days of this Nautapa with rains, and then floods and droughts and urbanization and conflicts. Of course, now as the population is increasing, we are facing pressure on our water resources, and once these water resources pressures are there, we are like okay, we will not allow the water to pass through any country that is downstream. First, we are going to meet our requirements, and that's of course leading to conflicts. And of course, sustainability is the key to it. Sustainable agriculture development, and of course, particularly the water resources. We use it in a way so that it remains for us and for our next generations also. So we require responsible and effective governance mechanisms. We require resilience of people, enhanced resilience of people, communities, and ecosystems. And of course, agriculture that fails to protect and improve rural livelihoods and social being is unsustainable. And of course, this can be achieved only by sustainability, by direct action to conserve, protect, and enhance the natural resources. And of course, when we talk of innovative water-saving technologies, the main point is we must be able to measure the water. Still, if we go to the rural side, this is lacking. Irrigation scheduling is still done on thumb rules. We are not adopting the advanced methods of irrigation scheduling. My area, my water. Of course, as talked by the earlier speaker, also Mr. Prashant, Dr. Prashant, we have to adopt circular economy of water also. Then efficient irrigation methods, another thing. And of course, crop genetics will play a good role in these water saving technologies, and use of disruptive technologies. And of course, effective irrigation water management begins with accurate water measurement. Water measurement is required to determine both the total volumes of water and the flow rates pumped. And of course, usage of uniform units of water. And of course, usage of uniform units of water and usage of water measuring devices. Actually, the problem is when we say that, okay, when we are into measuring the canal flows, we are still using those FPS system of units. And of course, we need to use the units, SI system of units only, or uniform system of units. And then anything that goes out into my farm or must be measured, so that the farmer must know that how much water they are applying for getting the yields. When we say this, it means the farmer will also know that they are not selling the produce, but they are selling the water. And when we say soil water irrigation scheduling can be based on soil water content, soil water potential, soil water balance, entering and outgoing water fluxes, plant water stresses, or canopy measurements. It can be based on this, and it can also be based upon the weather parameters. And of course, this is the most commonly adopted method for calculating the evapotranspiration and ultimately calculating the irrigation water requirements. But then the problem with this method is there are a lot of parameters that have to be noted down, and we require a good weather station for measuring all these parameters. But then in most of the places in the country, this is not available. So we tried a method, AI-based method, in which we took different combination of input weather data. In scenario 1, it was temperature, minimum maximum, relative humidity, minimum maximum, sunshine hours, and wind speed. In scenario 2, it was minimum maximum temperature. Here we leave left RH, and in scenario 3, it is minimum maximum temperature and wind speed. In scenario 4, it was then we left this wind speed, and in the last scenario, it was minimum maximum temperature and sunshine hours only. And of course, we developed the AI-based algorithm, and we partitioned the data in a way that 70% of the total data was separated into training data, 15% used as validation, and remaining 15% was used for testing for every representative district of agroclimatic zone. So we did this study, and for different zones of Punjab, and found the mean ET0. And of course, this shows for Ludhiana only the different scenarios. You can see that even the minimum value that we got of R square was 0.917. And if we go by those empirical formulas which we were using earlier, even something around 0.7, we take it as a very good value. And of course, with the minimum number of parameters, we get the value of perfect value of ET0, and that can be easily incorporated into the systems, and we can find out the irrigation water requirement on the daily basis or weekly basis, whatsoever it may be, which we are still doing on the basis of thumb rules. I'll not go much into it. So this is the simulated ET0 for January to February 2021 month using ANN for Ludhiana. So another thing is my area, my water. We have to follow the circular economy of water. Water extraction from we can have water from either from the groundwater or the surface water or whatsoever rainfall that is being that is falling on the in my area. Each thing has to be accounted for, and then it has to be recirculated again and again in my system only, so that I do not waste any amount of water. Right, till now we are following only the linear economy of water. The linear economy means whatsoever comes to me, we use it and let the polluted water go out of my system. I give you an example that in Chandigarh, they are using the capital city of Punjab and Haryana. They are using tertiary water for irrigating the these parks. And by simply investing only 72 crore rupees, they are able to save around 22 lakh gallons of water every day, and that too a good quality water. And of course, it is a transition from linear economy of water to circular economy of water. Then, of course, other methods are efficient irrigation methods, micro irrigation systems, alternate wetting and drying method of irrigation in paddy, then conservation tillage, automated irrigation systems. They can again be a game changer, and of course the innovative practices. Of course, in India we are doing it, but then still micro irrigation systems have to go up long way, so that we will be able to increase the efficiency of the irrigation systems in the country. And of course, we did a lot of experimentation at Punjab Agriculture University on micro irrigation, on drip irrigation and fertigation, and we recommended almost on all the crops and cropping systems of Punjab. The thing is, in Punjab, it is the investment that there's the reason why this system is not getting popularized. But then of late, the government has risen up and taken the responsibility, and now we are doing it in a focused way. But then, of course, even if someone is not doing it, but then even then we have to be technology ready, so that whenever there comes a chance or whenever there is an investment into the systems, we are technology ready, and it can be easily transferred to the farmers. And then there is another technology called low flow, low pressure drip irrigation system. This is a kind of system where the pressure requirement in case of pressure requirement for drip irrigation system becomes very low. In earlier systems, now I've started saying conventional drip irrigation system and low flow, low pressure drip irrigation system. In earlier irrigation systems, the pressure requirement was around at least 15 meters of the head of the pressure is required. But then in case of this systems, only 60 centimeters of the head is required, and we can irrigate any expense of land. And earlier, when we say that earlier we were saying that okay, with low flow, with low pressure drip irrigation systems, at the most 1,000 square meter area can be irrigated. But with this, it depends on the flow. If I am getting a flow for 5 acres, so I can irrigate a 5 acres land with the help of this low flow, low pressure drip irrigation system. And of course, the only requirement for this is the tabletop LEDs. Low cost, energy saving, zero investment on filtration system, no external energy sources required, can be operated with heads less than 1 meter, particularly in the canal command areas where around 6 to 7 feet head is available. These systems can be easily integrated into the irrigation systems, and the farmers can have the advantage of micro drip irrigation system. This is the crop of paddy. This is the crop of wheat in at PAU on low flow, low pressure drip irrigation system. Then we also did some work on drip irrigation in paddy in Punjab, exploring the new horizons. And of course, when we did it, it saves around 48% of water, and that is huge. And recently we shifted to another technology, that is alternate wetting and drying using drip irrigation system. And of course, that saved up to around 36% of water. But then, of course, saving 36% of water in from around 150 centimeters, that is also huge, and will help save declining water table. But then the problem with this system is, there is one problem: it requires a huge investment also, which is not required in the case of low flow, low pressure drip irrigation system, which comes as a lesser cost. But then still it cannot be like included into the subsidy mechanism, because in those systems we require BIS certified pipes, and those pipes are thin-walled pipes which are used in this low flow, low pressure drip irrigation system. So we are still struggling for that. Let's see if something improves or comes up. And then there is no yield penalty, rather it's a yield increase, and water use efficiency is quite high. And of course, it comes with the power saving also, almost 25% of energy saving. But in case of low flow, low pressure drip irrigation system, if we use it in paddy, it is around 48%, because there we are not using the systems, there are no head losses. Then alternate wetting and drying in paddy. And this is another technology which was given by PAU. And of course, you can see around 10 to 12 to 20% water is saved. But then, of course, if this technology coupled with the drip irrigation system, we can save around 36% of water. Then, of course, crop genetics. That is also development of drought-tolerant varieties. That is another thing which we can develop, and of course we can save on water. And then short duration varieties of water. This is another innovative thing, like PR 126. Normally, PUSA 44 takes around 140 days to harvest, but then PR 126 takes around 100 days to harvest, almost 40 days less, and that ultimately results in lesser water consumption. And then, of course, rainwater harvesting techniques. We are still not harvesting the rainwater. You'll see that people, particularly where they are this pumping arrangements are there, they are not saving, they are not harvesting the rainwater. It has to be harvested. And of course, we have seen it at many places: surface runoff harvesting, underground tanks, rooftop rainwater harvesting tanks, and check dams and contour bunding. Of course, in our scheme, in our project, All India Coordinated Research Project, we are working on check dams made up of either plastics or recycled recycled plastics. And of course, these dams are very easy to check dams are very easy to construct, and can be like constructed at any place where where the site is suitable. And of course, this helps us. This is a response to the climate change, such as erratic rainfall patterns. Rainwater harvesting provides a dependable solution for alleviating the effects of water shortages. I tell you, sometimes we feel that when we are using conventional irrigation methods, what happens is, if we say that, okay, 4 irrigations are sufficient, and normally the canal water is supplied accordingly. But then if there is sudden change in temperature and sudden rise in temperature, which has happened 2 years ago, there was grain shriveling. And the farmers who were doing who were raising wheat crop on sprinkler system or on drip irrigation system, there was no grain shriveling and ultimately no yield loss. So if we are using such modern irrigation methods, we can easily manage such challenges. And of course, water recycling and reuse, I have talked earlier also about it. And we have to recycle our wastewater and not let anything go out of the system. Then another thing is desalination technologies, particularly in the arid areas. The ground or the downstream of the canal command areas, the groundwater is arid. The groundwater is brackish, and because we start adding water, it also results into the drainage problems. If we start using we have to manage even the this brackish water, so we can use the desalination technologies, and we did trials on in the Center of Excellence, Indo-Israel Center of Excellence for cultivation of fruits and vegetables using brackish water. There we have used this desalinated water by getting desalinated water using reverse osmosis process. And we gave a good number of recommendations, particularly the farmers who could not get this canal water in these challenged sites. This is a good solution for them. They can use this water. They can desalinate it, the groundwater, and use it for irrigation purposes. And the last slide, the disruptive technologies. Of course, Internet of the Things, field and equipment centers, I will not go much into it. Drones and crop monitoring, that also technology. And then machine learning and analytics. And the last one is vertical farming and hydroponics, particularly for the water challenge sites. The vertical farming and hydroponics is the only solution where we can raise the same produce with the 5% of water which what we have used outside. And this is a technology which is required, which people are working on. And of course, in hydroponics, we have also used the brackish water for raising the vegetables, particularly these tomatoes, and then lettuces and some salad basils, and the results were quite promising. And of course, these technologies will help. These innovative technologies will help in managing the climate changes that we are facing. And of course, we are doing some trials on plant factories also. Normally, we get only 2 crops of lettuces a year, but then when we are using these plant factories, we can raise even up to 11 crops a year. That is the wonderfulness of these systems. I think I made my point. Thank you. Thanks a lot.
Thank you, Dr. Sharda, for very informative talk related to soil, water, and especially agriculture. Some participants might be having some queries they can ask. Meanwhile, I wish to inform the participants that Environment e-quiz link has been sent on the chat box as well as on mail, and you can participate. It is open for 15 minutes only. From 1 p.m. to 1:15, you can participate. So, any participant having any query with Professor Dr. Sharda? I have one query, sir, regarding saline water or brackish water use especially in the pipelines is there any chance of contamination of microplastics as compared to the normal water? Is the salinity or alkalinity of the water, is there any study related to that aspect?
I have not done those studies actually. But then, of course, now if we are able to measure the microplastics and nanoplastics even, so that study can also be taken up. Na? Even people are nowadays asking that, okay, we are using pipes, particularly these PVC pipes for lowering as a casing for our tube wells. Will that also lead to the microplastic or nanoplastic pollution? It is still debatable, but then we have to work on that.
Okay. Any participant? Dr. Srivastav, NBRI. So I think.
I am here, sir. Good afternoon.
Okay. So thank you, Dr. Sharda, for sparing your valuable time and giving your insights on the different aspects of use of plastics in agriculture, and Academy ANRCM Lucknow is very much thankful to you for sparing your time, for having a good discussion during the program, and your association with the academy in future also we expect. So thank you. And Dr. Arya,
Yes, sir.
please thank Dr.
Yes.
Dr. Sharda and invite the next speaker.
On the behalf of ANRCM, I am very thankful to Dr. Rakesh Sharda, sir, for sparing his valuable time. We had the opportunity to interact regularly. We have the anecdote of sharing the experience in 2011 when Dr. O.P. Chaudhary conducted a 21 days training program. And we are very fortunate that just 3 months back, Dr. Sharda was in Jammu. And there also we had the interaction, and our Honorable Vice Chancellor was also there. And on the behalf of the Academy President Dr. A.K. Singh and Dr. Sanjay Arora sir and his core team, we are very thankful to you, sir. And already the request has been made by Dr. Sanjay Arora sir that we want an expert of your caliber to be part of the Academy, because by your vast experience, the Academy will definitely learn new things, and we are here to serve the new scholars. Our aim is to tap the knowledge of the new scholars to equip them with few of the area where there is less knowledge, and we want to work as a bridge between the scholars and the academicians. Again, sir, thank you very much. And moving on, thank you, sir. And moving on now, our next speaker is Dr. Arjun Singh, sir. He is a senior scientist. His specialization is in agricultural microbiology at ICR, Central Soil Salinity Research Institute, and vast experience.
I think Dr. Srivastav, Pankaj Srivastav is ready. We can, as per Dr. Arjun, we can wait, na?
Yes, Dr. Pankaj will present.
Okay.
Okay. So, sir, please, I'm short of his Vita, sir.
I have sent on your mail, please. Check.
If you have the Vita, sir, Sanjay Arora,
Okay.
sir, you can read. Yes.
Okay.
Yes, sir.
Just-
Sir,
just-
one last thing I want to add, sir. The important thing is that the last lecture by Dr. V.N. Sharda, it is such
No,
a great.
not V.N. Sharda, Dr. Rakesh Sharda.
Sorry, Dr. Rakesh Sharda was such a great importance that we are facing this problem in Jammu and Kashmir, the Indus Water Treaty. It is a national issue nowadays. To conclude that, thank you very much, sir.
Okay. Just a minute. All the participants should try to participate in the quiz as we will be closing at 1:15. So I welcome Dr. Pankaj Kumar Srivastava.
Thank
He
you,
is
sir.
very renowned scientist in the field of environment management, and he is a senior principal scientist and head of the Environment Technology Division of CSIR, National Botanical Research Institute, Lucknow. Dr. Srivastava has significantly contributed to the research domain of environmental monitoring and assessment of soil contaminants. He has 22 years of research and teaching experience in environmental science and technology and has comprehensively mapped arsenic contamination in agricultural areas covering 7 agroclimatic zones of Uttar Pradesh. He has a very vast project on that aspect. His R&D includes especially microremediation of arsenic contamination in crops and phytotechnology for controlling contaminant ions and organic compounds in polluted matrices. He has developed a novel microbial formulation of indigenous soil fungal stains and demonstrated its efficacy in mitigating the arsenic contamination of paddy soils, especially in the areas where the contamination is very high. Dr. Pankaj is coordinator of NBRI EIACP program, Center of Ministry of Environment and Forest Climate Change, 2 national level green skill development program approved by NCVET, Government of India, under the Skill Mission of India. He has conducted, and I was fortunate to be associated with that aspect with Dr. Srivastava. He has developed a unique Green Planner app for stakeholders and society, providing an interactive database of air pollutant ameliorating plants. He has good scientific credentials, which are reflected in the several grant in aid projects he had handled as principal investigator, sponsored by SERB, DST, DBT, Ministry of Environment, Government of UP, and yielded R&D outputs, especially arsenic mitigation to agriculture and remediation of other pollutants. Dr. Pankaj has, to his credit, more than 80 international publications in high impact factor journals in the field of environmental sciences. He has published 8 book chapters and received several awards, including the Fellow of the International Society of Environmental Botanists and Fellow of National Environmental Science Academy 2022. He is a dynamic personality and working in a national institute at Lucknow. I request him and to present his talk, and we are thankful to him for accepting our invitation to join this program and deliver his talk. Dr. Srivastava, please.
Thank you, Sanjay sir, for your kind words, for introducing me to the audience. And first of all, I want to render my sincere thanks to the Academy of Natural Resources Conservation Management, Lucknow, and the senior people, Dr. YP Singh, Dr. Sanjay Arora sir, Dr. Arya, and Dr. Arjun. And sorry, Dr. Arjun, I am just sitting in between you and audience.
No, sir.
So I
It was
will
your turn, sir.
complete. No, it's okay. So it's a very pertinent webinar which Academy is hosting on the topic of combating plastic pollution for a healthy environment on this great day. So let me share some of my thought to you. And my slides are visible. Just Dr. Arjun or Dr. Sanjay, please let me know.
Yes, it is.
Yes, sir.
visible.
Yes, sir. It's visible.
Okay. So, coming to the issue of this microplastic, which the earlier speaker was deliberating, plastic was invented as a boon. Then,
Participant, please mute yourself. Otherwise, yes, I am muted.
so the history of plastic, it's a great invention of humankind, and it served a great purpose conserving our natural resources And its utility, it's mold, easy to mold and easy to create something useful for the mankind. It's a great invention. But if you see the graph, how the plastic production goes up globally, so more than half of the plastic ever produced have been made since 2000. That is 56%. And if we forecast the data of this production of plastic globally by 2050, so it is going up, and it's a estimate of a report of Plastic Europe report is published in 2022, that by 2030 it is projected to be 600 million tons. So it is the status of plastic production, how we are going to use this plastic. Slides are moving, Dr. Arjun? Yeah, okay. So now plastic has been invented, then we are using the different plastic product in our daily life. So where it goes after use, the plastic in the environment. So if you see here, most of the plastics are mismanaged and they are directly going to the part of environment. A little of that is the part of landfill. Some of plastic products get incinerated, and only less than 15% of plastic waste generated we are used to recycle and converting into the reusable item. And what happens to the rest of the part of more than 85% after being released into the environment? Then it just degraded, weathered, fragmented, and breakdowns in the tiny particle that we are calling nowadays as microplastic, nanoplastics. And it finds its ways in all the spheres. If we talk about the atmosphere, hydrosphere, lithosphere, everywhere these tiny plastic particles are present nowadays. Coming to the concept of microplastics, it's a recent term coined by Richard Thompson in 2004. And two kind of microplastic we may have. That first is the primary microplastic, purposely manufactured in the small sizes, mostly for our plastic care products, personal care products. And secondary is just getting deteriorated, fragmented, and weathered from the larger plastic being used for the other purposes. And both biotic and abiotic factors, they play their role in converting the major plastic particle into the lesser shape. And this microplastic, it's a synthetic solid plastic particle in the size range of from 5 mm to 1 micrometer, and lesser than that we call as a nanoplastic. So what has happened globally for the last 20 years? It's era of microplastic just begins. And then the first report came of transport of the chemicals, then NOAA, this majorly working of the plastic debris in marine ecosystem. They come up with some international workshop, and they reported the plastic in the marine ecosystem, in the shoreline, the beach areas. In 2019, there's a first report of presence of microplastic in human stool, then reported from the Mount Everest, and down the line up to last year, 2024, the major policy decision is just shifting their orientation how to end the plastic pollution today as a internationally legally binding instrument. And our Food and Agriculture Organization, they also come up with the code of conduct for agroplastic last year. It's under development, yet to be vetted globally. But now, globally, the sincere and serious efforts, they are just meeting to convert what to be done at the policy level, what to be done at the research and development level to combat this tiny plastic particles. So majorly, marine ecosystem was searched out initially, but nowadays, as we told earlier, all the sphere of our environment, atmosphere, then hydrosphere or freshwater ecosystem, marine water ecosystem, then soil ecosystem contaminating to the agricultural crops. We are talking about the contamination possibility of this microplastic in the agriculture soil. So this year, starting from 2020, major research focus has been shifted towards the mapping, developing the methodologies, and what are the sources these are contributing microplastic in the ecosystem. If we talk about the in a entire broader perspective, then product manufacturing, product use, product maintenance, and product disposal. These are the four different categories. They are releasing the microplastic, nanoplastic into the environment at their own cycle. Then, if we talk about the major sources of microplastic in agro ecosystem, so this biocell application, advocacy for using wastewater for irrigation, plastic mulching, it's a very good thing, but now it's a major factor contributing microplastic, nanoplastic into the agro ecosystem. Then weathering of tires and atmospheric deposition nearby this open dumping site that we called as a so-called sanitary landfills, but majority these are open dumping grounds. They are just adding this tiny particle in the transboundary approach, like the atmospheric movement, and as well as the surface runoff from these open dumping site to the nearby agriculture fields. Then slow release fertilizer. So these are the known potential sources of microplastic. I will not touch upon this because the next speaker, Dr. Arjun Singh, will elaborate at a larger length. But we have the sources of plastic in our contemporary agriculture. If we talked about the crop production, if we talked about the livestock farming at ICR or the associated institutions, so these are the main potential sources contributing to the success of agriculture in one hand, and nowadays these are the potential sources contributing this tiny polymer particle into the environment, as well as especially in the agro ecosystem. If we see the diversity of this microplastic, if we talk about the shape, if we talk about the polymer types and colors, it's a huge diversity we have searched out. And pellet, film, spheres, fragments, fiber, foams, these are the different shapes. And then this polymer type of this PET, this polyethylene, whether it is high density, low density, then PVC, polypropylene, polystyrene, and other kind of this polyactic fibers and nylons and fiberglass. So these are the major polymer types. So there's just a glimpse of diversity of microplastics. And below 1 micrometer, that we are calling those particles as a nanoplastic, these are the major cause of concern. So just giving you the range, a glimpse of the size ranges of macro, meso, micro, and nano level of microplastics. Then if we talk about the aging of this plastic particle under the UV radiation, the thermal, physical aberration, biodegradation, chemical oxidation. So these weathered microplastics as compared to the virgin polymer particle.
You attended, yeah, participation.
These are just creating these microplastic, weathered microplastic as a vector.
Sending by Sunday on the email.
Dr. Arjun or some associated one, if we have some.
I'll just check it. I'll just check it.
Okay, some background noise is there, so that can be taken care. So fragmentation, cracks, then additive release, then biotic attack, altered crystallinity, this altered physical property changes, formation of oxygen functional groups, if we talk about the carbonyl index of these polymer particles, and then alloying effect, this created these microplastic particle as a vector to attract the added contaminant onto it. So as it goes down from 5 millimeter to up to the nano scale, then the spectrum broad range exposure of these plastics goes down up to the crustacean, annelids, arthropods. So you see the diversity and the severity of the lower size ranges of these polymer particles. If it goes down, that it has the tendency just to infect not only the fishes, the avians, but the crustaceans, mollusks, annelids, earthworm. So reports are there globally. So it's a very serious business because it will disturb the harmony of environment or the natural carrying capacity of any ecosystem, and is a huge potential of transfer of these polymer particles at the different tiers of food chains. This just to give you the glimpse. If we start from our head to the toes, all the body parts, the researchers has reported the presence of microplastics or nanoplastics in different body parts. And three major route of exposure is that is through inhalation, through direct intake, and through dermal absorption. Then it's a cause of human concern. Why we are talking more about the microplastics? Because we are at the risk, we are at the threat level. So these are just a glimpse of new research papers. They are publishing day by day by our medical experts and experts dealing with the human health and toxicity, ecotoxicity. So you just see that the human lung tissues, then bone marrow, and everywhere in mother's milk, even in the fetus, they have reported. And Toxic Links just released this report that all the Indian salt and sugar brands are having the microplastic into it. And it's a global scenario where everyone is doing research, starting from the waste management to human health, ecotoxicology, ecological risk. But in India, majority of the work is related with the human health and for the water ecosystem. There are very much less paper considering the soil ecosystem at place. So our Honorable National Green Tribunal taken suo motu cognizance and just giving the directives to the different ministries and the departments to take care of this pertinent burning issues at the national level. So this FSSAI, they have initiated one national mission project where our sister laboratory, CSR IITR, Indian Institute of Toxicological Research, is the counterpart of that. And we, with the Indian Institute of Soil Science, just push forward this issue at the ICR level. And I hope that ICR or Minister of Agriculture may take up some national mission project for safeguarding our agriculture or the soil system for the contamination of microplastic into it. So coming to the detection methods, so as of now, there's a very little advancement for mapping of microplastic in the soil as well as in the plant ecosystem. But definitely this microscopic analysis, then thermal analysis, we are using the energy spectrum, this mass spectrum, and other techniques. So now FAO is in the position to develop and publish a globally harmonized protocol for mapping of microplastic in the different kind of soil types globally. Some constraints are there. First of all, we are lacking the baseline data of microplastic contamination in our country. The reason is that the challenges behind the measuring and quantifying microplastic in our agriculture soil is related with the heterogeneity of soil composition in this country, then variability of microplastic in terms of shape, size, colors, and polymer composition, invalidated methodologies for extraction and quantification. This sporadic research papers are there, but there's a lack of uniform analytical protocol, making it difficult to compare the result from different studies. And this country definitely needs some center of excellence with a state-of-art facility for all those analytical resources at a common place that will ease our R&D. So keeping in mind, we just attempted to develop a modified methodology for extraction and quantification of microplastic in soil for this size range of a small 10 to 100 micrometer and larger size of microplastic up to the 5 millimeter. And what we have done, we have validated our methodology with sequential step, and we got the more percentage of spiked recovery of this microplastic that we have spiked into the soil system. If we keep the organometric digestion as a first step, and then go for the density independent separation. So this paper has been published in Nano Impact, and using these methodologies, we have mapped 8 different land uses of this northern India. There's a wetland, industrial area, then municipal city areas, municipal waste, open dumping site, and agriculture field near those dumping sites, and agriculture fields with the plastic mulching, then urban area, peri-urban area, and rural areas. And this is the scenario that we got up to the 7,000 of microplastic numbers, particles per kg of soil we have reported at the dumping site. And not only in the first data, we have we did the stratified sampling, and you just name the land use system, and at different strata up to the 20 to 30 centimeters, the perfect root zone for our annuals or the major cropping system. It is being contaminated. The presence of microplastics is there. So this is just a technical data, and the paper is under revision, and we just computed this diversity index just base. So this polymer composition, shape, color, sizes, if it give these 4 determinant considering the diversity index and the evenness index, this polymer composition putting at a number 1 in the determinant level, if we talk about the scale of microplastic presence in different land use systems. So what will the fate of microplastic in the terrestrial ecosystem from sources? It goes through the surface runoff, the atmospheric deposition and sedimentation. It will go downwards, vertical as well as the horizontal movement under the gravitational force and the surface runoff. It is going to be in the part of this soil fauna, and root zone is getting contaminated, and this nearby freshwater ecosystem or any water body, it is getting contaminated with the huge presence of these tiny particles. And through plowing, harvesting, then water infiltration. So this just give you the glimpse of how this plastic particle originated from the source and now becoming a transboundary problem in different years of environment. Again, we are at the position to map the localization of microplastic in the cereals and vegetables. So, no baseline data of magnitude of the problem. If we talk about the different cereals and vegetables, we are generating the data in the vegetable, especially in the leafy vegetable of this northern India part. And we are also in the process to compute the different risks under the risk assessment. So this threshold value we can fix if we talk about for in the future food security as well as the health conditions, human health conditions. Additive to the plastic for different plasticizers, flame retardant, heat, UV stabilizer, biocides, colorants, slip agents, they are just being put into the formation of different plastic products to give strength or the usability for a particular specific purpose. But these are chemical additive getting released during the weathering and degradation process of this pollutant particle and creating the added toxic effects. Again, as I have explained earlier, meeting में है थोड़ी देर बात करो. So, if we talk about the soil contaminant present in any soil, like the heavy metals, this organic contaminants, antibiotics, and pathogens, these are the added contaminants, you can say, using microplastics as a vector. And this co-contamination stage is very, very deleterious for the plant productivity, quality of the plant yield, as well as the human health. And different hydrogen bonds, then hydrophobic partitioning, this pi-pi interaction, van der Waals forces, and these are the different chemical interaction and bonding. This microplastic tiny particles, after weathering, they are just conjugating with these contaminants present in the soil and just aggravating the problem of microplastic pollution in the agroecosystem, as well as if we talk about the human health. So initially, we try to understand and publish this comprehensive review for unraveling the emerging threats of microplastic in agroecosystem, and in that, what could be the alteration of agroecosystem functioning if we are not going to take the immediate step for prevention as well as the cure of microplastic in the agroecosystem. So we discussed all these issues in that review, and it is available in the open access. If we talk about the toxicological impact of this fauna, the bovine products, as well as the earthworm, then the avians. So it is just shifting the load of microplastic getting biomagnified and putting different kind of oxidative stress, and they are the part as a bioaccumulation one, and it's again the secondary route of exposure. If we consume this contaminated bovine product in our system of contaminated milk, meat, eggs, so it's again an avenue of research of the related scientists. And this is the three major route of entries, how microplastic goes into the plant. First is through stomata after deposition on leaf, and second is through the root, and it is just got the upward movement under the transpiration pull, and majorly through apoplasty, symplasty, and the cracks during the growth of this newly developed roots. These are the potential sources of microplastics. सर एक वेबिनार में हूँ, आप एड्रेस लेके अंदर जा जाइए, वहीं पे खड़े हुए हैं, मेन उसमें खड़े हुए हैं, डोर पे पूछ लीजिए। संध्या, बाहर कोई गेस्ट है, उनको अंदर ले आओ। सॉरी। So we conducted, we just started using the spinach and other leafy vegetable, and we are going to map what is the major route of entry of this nanoscale plastics, and how it is getting localized in particular cell organelle, and what would be the altered growth response and physiological responses, which is going to hamper the quality of the plant produce. So we have initiated these experiments, and we are using this dyed polymer particle and conducting the hydroponic experiment, and then we'll conduct this microcosm mesocosm trial at our institute. So these are some reports that had published globally, but what we see is that mostly they have conducted in the controlled condition. Very few data that we have received from the field level stage. बाहर एक गेस्ट आए हुए हैं, उनको बोला है अंदर लाने के लिए। अच्छा, आप नीचे चले जाइए, डॉक्टर संजय हैं एग्रीकल्चर डिपार्टमेंट से, स्लैब में बैठे हुए थे, बुला के अंजू के पास बैठा। And again, it is very well established if we talk about the reproductive system, respiratory system, digestive system, nervous and cardiovascular system. Each and every place or the body organ, it is getting deposited this tiny polymer particle while upon ingestion of these contaminated food products. And this again one area of R&D that we have initiated at our institute. So we are going to utilize the concept of aggregation, immolation, and entrapment of this nanoscale particle, and we are in position to convert this nanoscale into micro and further mesoscale. So it may restrict the entry of this contaminated particle into the phytomass. So this one avenue, and for this we are using this humic acid, and we have conducted the experiment using the polypropylene, polyethylene, and PET. So first, this batch experiment result that we got, and secondly, we are just initiating or upgrading this finding into the macrocross experiment. Again, this some plant growth hormones like breastnonsteroid and jasmonic acid, they just downregulate the expression of aquaporin. These are the major pathway of entry of this nanoscale polymer particle into the crop system, and not only the breastnonsteroid or jasmonic acid, we are conducting the experiment of having more of this plant-based chemicals, which has tendency to reduce the toxicity of this nanoscale microplastic by altering the entry route of this polymer particle into the plant system. And again, my colleague Dr. Anju Patel, she has started of utilizing the potential of organic coagulant and natural coagulant for the removal of microplastic with the approach of coagulation, flocculation, and sedimentation. So it is at a very nascent stage, and we hope that down the line in 3 to 4 years or 5 years, the NBRI would come up with some potential technologies. Our microbial technology division, led by the microbiologist, they are working on this biodegradation concept of microplastics, because we are gifted with the natural microbial strains, having the expression of this extracellular enzymes involved in the degradation of different polymer particle into the their monomers and up to the carbon dioxide and hydrogen that goes into the TCA cycle. So our microbial technology division is working on that. So in nutshell, what need to be defined, challenges to overcome and need to implement, we have just giving this scenario in our published review of literature. So first problem is the hazard identification, the identification of potential sources, then morphology and types of microplastic in our ecosystem of diverse soil type in the country. And then what comes under the exposure, the quantification, the spatial temporal distribution, the quantity and threshold limit, degree of toxicity, their interaction with the biotic and abiotic component, what would be the mechanism of interaction with biological organisms. So we need to establish some risk factors, what would be the threshold we can cope up with. And finally, with the mitigation and remediation, for me, prevention is the first step. So different education programs, awareness programs for all the tier of society need to be conducted by the scientists, aggravating this, just giving the glimpse of this burning problem to the society. So discourage the use of single use plastic products even, and shift to the alternatives, then developing the detection kits and markers, some stringent laws and natural remediation methods need to be developed by the scientists. So and this again, the prevention is better than the cure. So it is in our hand. At least we should completely phase out this single-use plastic, even from our daily lifestyle. And Dr. Arjun will tell more about the how we can phase out this plastic products of agriculture use. So I leave this issue to be dealt with by Dr. Arjun. So thank you all. Thank you, Academy, and specifically Dr. Arora giving me the opportunity.
Thank you, Dr. Prashant, Dr. Pankaj, for very elaborate uh, your experiences, especially not only in the field of arsenic, but in the field of plastics, as you are working on that aspect also these days. Any query from participants? Participants, it is a high time. Most of the participants are basically research scholars and students, and it will be beneficial for them if they interact. It will be more easy to clear their doubts and any issues. Any participant?
I urge the young scholars to kindly ask the questions. The purpose of the academy was to organize a webinar to have a two-way interaction.
So if not, many of them have participated in the e-quiz. We are thankful to Dr. Pankaj Srivastava for
Welcome.
sparing his very valuable time. He was very busy today. They were
So
at
let's-
NBRI. They
Indeed.
were organizing a program. I requested him that you please spare, but I think this is the first time he has joined our academy activity, and hope we will
Anytime,
be
sir.
having
Anytime. Yeah.
having a good collaboration in the future also.
Definitely, sir.
So, on the behalf of academy and on my personal behalf and organizing committee, we are thankful to you for giving a very good lecture, and sir, this society or this academy is very small one, but we have diverse members, not only from UP but from 17 states, and most of them are young professionals and basically related to agriculture and environment, and hope your presence would have been beneficial for them, and we expect the similar cooperation in future also. Thank you very much, sir. Thank you.
Definitely, sir. Thank you so much, Dr. Sanjay and the academy officials. Thank you.
Thank you, sir. Thank you. Dr. Arya, please
Yes, sir.
continue.
Shall we move to the next speaker?
Yes.
So with
There
this,
is announcement that participants, you should keep yourself mute and wait till the end of the program, because we will be announcing the results of the e-quiz. Dr. Anshumal Kohli will announce at the end. So wait till that, and all the participants who have participated in this webinar will get the e-certificate, and the winners of the quiz will also get the e-certificates for the quiz. So, Dr. Arya, please continue.
sir, again on the behalf of academy, I am highly thankful to the eminent expert. Special thanks to the expert on behalf of Dr. Atulji, Dr. Sanjay Roda sir, Dr. YP Singh and his core committee. We are very thankful to you, sir, because of your busy schedule as elaborated by Dr. Sanjay Roda sir. Still, you have given us the time, and it was a very interactive lecture where you have touched upon the various spectrum of the microplastics, especially with the human health, which is a cause of concern for everyone around. Even in the rural area now, people are getting aware about their health. So we are very thankful to you, sir, and we look upon in future to work with you through our academy, and we want your guidance also, sir. Moving on, sir. Now our next eminent speaker is Dr. Arjun Singh. He is a senior scientist, and his specialization in agriculture microbiology at Indian Council of Agriculture Research, Soil Salinity Research Institute. With 11 years of research experience, his work focuses on plant microbe interactions, microbial ecology, and microplastic. Dr. Singh has made significant contribution to microbial studies, particularly in deciphering the rhizo microbiome associated with indica rice and wheat. He has also collaborated in the development of numerous microbe-based technologies for rapid composting, in situ paddy degradation. The paddy degradation is a huge challenge. Sulfur oxidation, high throughput DNA isolation techniques. Currently, he is pursuing research on microplastic contaminants, focusing on their occurrence and distribution in agricultural soil. For this, he has secured funding from DST Serve India. His research has been widely cited, reflecting its impact on the field. To date, he has published more than 40 research articles with about 1161 citations. He has collaborated with leading researchers from international institutions as well as national institutions such as University of Newcastle, Australia, Indian Agricultural Research Institute, New Delhi, and NBAM, Mau. I request Dr. Raju Singh to kindly deliver his lead talk. The podium is yours, sir. Please.
Thank you, Dr. Vivek, for the introduction. And kindly that I'm not able to share my screen. Kindly.
What is the issue coming?
Sir, let me try once.
Try. Open it first. First, open the PPT. Don't share the this one.
Okay.
Unshare it and then open the PPT and then share.
PowerPoint is open, sir. And again, trying to share it, sir. Is it coming, sir?
Yes, it is coming.
Is it coming as full screen now, sir?
No, yes, now it is okay.
Okay. I would like to express my heartfelt thanks to ANRCM for inviting me to deliver this talk, and ANRCM is like our homegrown academy, and not taking much of the time for all the participants, I would like to briefly go through what I'm going to present today. So the allotted topic of my today's talk is on agriculture plastics, sustainability and impacts. Like how come that agriculture plastics, which has come to in picture from last 70 years in our agriculture food systems, has now becoming a kind of risk for our crop production and the associated microflora and macroflora of our soils. So we will take up few of the case studies from the global case studies, and also what we have done, what our lab and my group has done till date to showcase that how come these plastics are having some kind of toxicity and associated problems. So already few of our senior colleagues has shared about many of the bigger pictures of the how much plastics production is there and how much it has become a permanent part of our economy. So some of the things will be common, but I will like to just quickly go through these things. Annually, it has been estimated that around 12.5 million tons of plastics products are available, which are being consumed in agriculture globally, and due to which there are after, if they have not been recycled or put to any other use, they are now ending up as a macro, micro, and nanoplastics in soils. Basically, these are the products which are being used in our agriculture system or farming systems. You can see that many of our agrochemicals like fertilizers, pesticides, they are all coming with plastic coating or they are mixed with some plasticizers. Fertilizer sacks, they are like popular ones. Then plastic mulch, most commonly seen around the farmers' field in northern part of India. Then many of the poly houses are all LDP polymers and SDP polymers. Then minorly like ear tags and then fishing nets, all are based on the plastic-based polymers. The major reason was that they are flexible, cheaper, and they can be produced in humongous number in a very small setup. And as per this picture, you can see that many sources of plastics are available in our farming systems, which can cause the buildup in and around our soils or in the associated riverine systems or underground water recharges. You can see that there are like biosolids. Biosolids are just MSW waste which has been composted. They might contain some of the plastic particles, which are undecomposed plastic particles. Then your polymer coated fertilizers and pesticides are there. Then mulch films, they are applied to the field, left over for the auto oxidation by the environment. The application of the UVs, shift in some kind of temperature, these all lead to the weathering of these particles, and the smaller particles in the size of micro and nano size particles can end up in the soils, as already discussed in the previous presentations. I'll just quickly look towards some of the data. It shows that the Asian subcontinent is the highest user of the plastic-based product in the agriculture system. And if you take the global perspective, that 359 million tons of plastics are produced in plastic-based products are produced, and among which 3 to 5% is being used for agriculture-based applications. And in that, as already I discussed with you, that mulch-based films and greenhouse films are the major plastic-based products which are being used in our agriculture systems. Based on the life cycle of these products, we can see that a plastic-based product has a life cycle of around 5 years, and afterwards, the problem is that they are just left over or they are just thrown in open systems, and because of like recycling mechanisms and all are lacking in our system, so they are just dumped anywhere. And over the period of time, due to the weathering and all kind of natural processes occurring, they start to disintegrate, and the smaller fragment, as per the cycle is seen by ingestion or by the passive uptake by the plants, it is entering into our food systems, and thereby the reports are coming up that it is present in our human blood, whether it's in milk, in the fetus, in the fruits, in salt and sugar. Everywhere you are finding some of the micro debris ending up in our foods. This is the first report by Thompson, who has discovered the microplastic particles, and based on his classification only, we are now, has devised a system of classifying the microplastics based on their size, their shapes, and their polymer type. So this was the baseline paper, and later on, many things are come up to how to like categorize these plastics based on their shape, size, color, the polymer type, and their various other allied features. So as per the size distribution of plastics after they are disintegrated, we can, like, when we are sieving our soils or we are filtering our water to identify the plastic polymers, you might find some of the particles which are in the range of 100 mm, which might be in the range of 20 mm, some in the range of 5 to 20 mm, some will be less than 5 mm. Based on that, we can categorize our plastic pollutants as microplastics, mesoplastics, macroplastics, or megaplastics. And further weathering of these debris can result into the formation of the submicron plastics, SMPs we say, or nanoplastics, NPs we say, because it's all based on the size-based classification. Then when we have looked into the research that what is the prevalence of the plastic polymers in the sediments, we find that the denser particles are more available in sediments, and low dense particles like polyethylene are more available in our aquatic system. But when we have analyzed our soil systems, we find that I will show you some of the data which we have generated in our studies, that more of PE and PVC particles are there in our soils as compared to the aquatic systems. Now, since we say that plastics are inert, then how come they are adding up to the pollution to our ecosystem? So when we studied their polymer structure and their features, we find that the plastic polymers have a crystalline and an amorphous region, and these when heated up at a certain temperature, the changing in the cross-linking in the amorphous region of plastics are absorbed. They can change into glassy or into rubbery types. Glassy means they will be more condensed, and rubbery means it will have a diffuse kind of structure. Under high cross-linking, if any kind of persistent pollutant are there, it will be absorbed in the plastic pollutant and it can retain into the surface for a very, very long time. But a diffusive polymer structure might retain the pollutant and it can release them quickly. It can easily diffuse them in the wherever environment they are found. So we can see that if the prevalence of polyethylene and polypropylene are there in our soils or aquatic system, parallelly we can observe that the associated pollutants like any kind of PHs or heavy metals, their prevalence will also increase simultaneously because of their high diffusibility. And the fluidity. So these concepts are also being taken care of while studying the plastic pollutants in the soil, that some of the key polymer types might be responsible for increase in the organic pollutants in the soils also. Then already some factors which are indeed play a primary role in interaction with the other pollutant kinds are the density of the polymer, its crystallinity, its size, shape, its color, its polymer type, its age, and molecular weight all play an important factor in increasing the pollutant, increasing the the concentration of plastic pollutants, persistent organic pollutants in the soils or in the water system. Now, few of the studies we will discuss here, that how come if that built-up of microplastic contaminants are there, how they will affect the physical, chemical, and biological property of our soils. So some of the works which were conducted globally, I have taken some part of the studies, and I found that if we increase the exposure of microplastics in the soil, we are finding that there will be decrease in the soil aggregation properties. That too, water stable aggregate properties will decrease as the concentration will increase, and also it has been linked to the shape also. So fiber type microplastics are causing up to 25% decrease in the soil aggregation property. So this is one of the mesocosm studies which was conducted. Then in another study, that how come if the plastic pollution built up is there in the soil, whether it will affect our hydraulic conductivity or not. So as the size of the plastics and the pore size of the soil textures, like we know that the sand has a larger pore space or as compared to the clay soil. So since more pore space is there in the sandy kind of soils, it can accumulate more of the microplastics in them, due to which the saturated hydraulic conductivity will be affected more in the sandy kind of soil as compared to the clay soils or the loamy kinds. So this is also one of the reports which shows that like the hydraulic conductivity is significantly hampered with the application of microplastics. Then we have also seen some of the reports which shows that the buildup of microplastics in the soil can lead to the increase in the soil pH also. Actually, it's an indirect mechanism. What is happening here is like when the soils are occupied by microplastic contaminants, the aeration of the soil is hampered, leading to the buildup of a more of an anaerobic or reduction in the redox potential, causing buildup of ammonical ions, which is indirectly responsible for increase in the soil pH. But it's like it's not increasing to like more of the alkaline or some of the. I feel that this works. Some of the studies should more studies should have been done, but still it is being postulated here that the buildup of MPs can also lead to the alteration of the soil pH. Then whether the buildup of the microplastic contaminants can also cause the increase in the global warming potential. So when the microplastics were applied in the soils, it was seen that the increase in the CO2 and nitrous oxide gases and methane gas was there from the soil environment, which is causing which is a like it's a potential study which if you can imagine it's like quanta, it's like they can play another part. They can be an important factor for the global warming in the near future. So definitely it's an alarming situation that plastic pollution creating a like situation of global warming. They have the potential to create a global warming. Now already which I have discussed earlier that the diffusibility or desorption of the heavy metals or any kind of pollutants is dependent on is directly correlated with the concentration of microplastics. Here in the study, they found that in the pure soil, the absorption of the heavy metal was more. But whenever the microplastics buildup was there in the soil, the desorption of heavy metals increased, leading to the increase in the concentration of cadmium in the soil, in the available fraction of the soil. So this is also a kind of concerning for the agriculture systems. Then whether the plastics can interact with the organic matter or not. So this study shows that definitely plastics can interact with the naturally occurring organic matter, and further they can be taken up by the plant system as well. So so this is like a passive movement of the plant uptake was there, and slowly it can build up in the shoots and the root system of the plants. Then this is one of our work which we have conducted in Australia, where we try to identify like how much plastic contaminants are there in the soil at different strata of the while taking the different depth of soil samples. In brief, if I can explain that these fields were being applied with the biosolids, and that too for a very long periods, like around 14 years or 15 years of legacy. And after and then we wish to see whether any kind of plastic pollutants are entering our soil system or not. So what we found that these fields were having very high amount of microplastic abundance was there. The particles number has increased. Around 1500 particles per kg of the soil was found in these fields, and these were the shapes and fragments and beads which were being detected in these fields. And also we find that these plastic polymers were having the adsorption of our heavy metals on them. So definitely their numbers have increased. Also, the heavy metal concentration was also found on their surfaces. So it was quite concerning for all of us. Then we tried to identify what kind of polymers were there in these soil kinds. So the most prevalent one was polyethylene copolymers and polyethylene, which was found in all the depths of these soils. And overall, when we identified that what was the fingerprints of all kind of polymers in the soil, then basically high amount of PVC, PMA, PP, PETP, all kind of polymers were there in this kind of biosolid applied soils were there. Then we also want to see that how the mechanism of weathering and aging of the microplastics was happening naturally. For that, we have deployed the microplastic polymers, and through electron microscope, you can see that small nanoplastics are also emerging from these plastic polymers. These are all kept in under the natural conditions and slowly built up of nano-sized particles were there. And further, in diploid polymer photograph, you can see the formation of biofilm communities was also there. So weathering is also happening, and in the weathering voids, the biofilming microbial communities are also trying to build up. Then being in microbial ecology, I just wanted to see that how the diversity is changing, whether is there any kind of shift in the plastisphere microbial communities. What we found is like control was having its own microbial flora as compared to the plastic microbial communities. So definitely some kind of unique microbial communities are being built up on these plastic polymers. And then next question came is like how the interactions of these plastisphere communities are taking place. So as per the, if we see the interactions, then we can see that under the controlled condition where there is no environmental extraneous stimulus of plastics are there is low modularity. That means different kind of communities were not observed. But when we have given a stimulus of recycled kind of plastics and virgin kind of plastics, we found that modularity has increased as compared to control, but there was higher modularity in case of recycled kind of plastics. That means more different kind of communities are being formed over the surface of recycled kind of plastics, which might have some implications in whether they are taking up, whether they finding it as a good niche to survive over there, or they might be like consuming them or so. We cannot comment at this stage. Then we also try to see that what difference was there as compared to control. Then we find that few of the genera has shown their high abundance in these plastic polymers. We can find Penibacillus, Salvibrio, Microlunatus. These genera have shown their occurrence significantly on the plastic surfaces as compared to the control group. And looking into the genomes, we found that these genera have some potential in degrading the plastic waste. So we can find many of the pathways which might help in like degrading these plastic polymers. Then we also want to see that how that soil macrofauna like earth forms are being affected if they are consuming the microplastic particles. Like they already report says that they can induce bioweathering, then whether its physiology is changing or not. How is their gut microbiota behaving under the influence of the various microplastic particles? So we find that as the size of the plastic polymers reduced, their numbers were increasing in their body, and also simultaneously the various stress enzymes also increased. And based on the genotoxic assay, we can see that DNA damage was also prevalent. Now, then we looked into the differentially abundant genre between the various treatment of plastic polymers. So we are finding some clues that Ramlibacter has came up as the most prevalent genre in the plastic-based polymer fetid earth forms, and maybe it has some role in maintaining the gut environment of the earth form when it is under fed conditions with the plastic polymer. Then we try to look up into the cross-domain uptake of microplastics, and we find that these polymers can be taken up by the plant system, it can be taken up by the fungal systems, it can be taken up by the earthworm systems. So definitely it's a dangerous situation that smaller the size and it can easily enter into our bodies. Genotoxic and assays has already proven that they have the potential for carcinogenesis. And lastly, as already that previous senior speakers have already shown that we need some technological innovations to have some, like, we cannot leave the plastics as such, but like we need to have the technological innovations to utilize them, to recycle them, to regulate their productions. We can use some of the like bio-based biopolymers for the production aspect. Some research should be there. Then we should take at most step that they should not enter our soils, our water systems, so that the cross-domain contamination can be reduced. And this we need to ensure at the policy level, at our level. And this is one of the project which we are running it at our center, where we are dealing with the impact and fate of microplastics in our agriculture ecosystems. And this is our international team where we have collaborated with them, who are helping us in doing this work. And thank you so much. That's it from my side.
Thank you, sir. I will request Dr. Sanjay Arora, sir, to kindly proceed with the results of the quiz and give an overview about today's webinar also. And then we will be offering the official vote of thanks to all the speakers. Yes. Dr. Anshuman Kohli, sir, you may please take the proceedings to the further level, please.
Yeah, Dr. Arya, can you see my slide?
Sir, yes, sir. The first slide is visible and the
Okay.
yes.
So good afternoon, everybody.
Good afternoon, sir.
We have had a very informative and learning experience today during this webinar. And as you all of you are aware that we had an environment e-quiz during the webinar for about 15 minutes. In this e-quiz, there were 80 questions, all multiple choice questions. This has been a regular feature of our webinars. We always, whenever we have a webinar, we also associate it with a e-quiz so that the student participants, they have another charm to participate in the webinar. Many of the questions during the quiz were what we all learned during the discourse by various speakers. So I would like to just announce the names of the winners, and I would also request the winners to switch on their video during the announcement of the results so that others can see you. Okay. So the results are on the screen. Can you see? Can you see the results slide?
No, sir. The first slide is only visible. I think.
Okay, just a minute.
Yes, now it is visible. Yes.
Okay.
Yes.
So yeah. So the first prize goes to Somin Mandal. If you can just switch on your video so that we can see you, Mr. Somin Mandal. The second for the second position there is Somin Mandal. Keep your video switched on, Somin. And for the second position there has been a tie. K. Bharati and Mohana Prakash AG. They have got the second prize. K. Bharati and Mohana Prakash AG. Both have got the second prize. And the third prize has been bagged by Vinothagan S. Vinothagan S. And a consolation prize to Chandan Kumar Panigrahi. You see, these 5 participants have scored over 87.5% marks. More than 70 marks, 70 questions were correct out of the 80 questions. And these have been selected to receive the e-certificates from ANRCM. So just over the next 1 week or so, you'll be receiving your e-certificates on your given email IDs. Congratulations to all of you. Not to say that all those who didn't find place in this, they were close enough, but then we had to announce only a few names as winners. So these are the results. Thank you. And once again, if any, these participants, these winners, if they can just show their face on the screen, we'll be delighted to see them. Okay, so congratulations to all once again. Thank you. Over to you, Dr. Arya.
So now it is over to Dr. Sanjay Arora, sir. Dr. Arora, sir.
I think Dr. Arya, you can conclude now.
Okay.
Dr. Arya has a scheduled class at this hour.
Okay, I will. So definitely, sir, I'm on the behalf of Academy. We were, I think I will use the word successful. That we had organized a very good webinar on combating plastic pollution for healthy environment while celebrating the World Environment Day. The broad spectrum of the speakers, the distinguished speakers, Dr. Prashant Shrivastava from Australia, Dr. Rakesh Shardaji from ICR CIFIT, Dr. Pankaj K. Shrivastava from CSIR, NBRI Lucknow, and Dr. Arjun Singh. All the speakers, they had navigated from one end to another end. shedding the lights on this important topic. And Academy is highly thankful to all of them for sparing their valuable time. In fact, Dr. Prashant Srivastava has to synchronize his timing because he is based in Australia, but he is very kind enough to accept the invitation on the behalf of Academy, on the behalf of our senior Academy office bearer. The organizing committee, Dr. YP Singh, Senior Vice President, Dr. Sanjay Arora sir, the Secretary of the NRCM, Dr. Arjun Singh, the co-organizing secretary, Dr. Anshuman Kohli, the pivotal role which you have played and you are playing from since inception of the NRCM, and of course to the president and vice president, Dr. AK Singh ji and Dr. DK Sharma ji. We are all thankful to you because of your constant guidance and inspiration. We are in a position to conduct such type of webinars. And recently, last month, we have organized a very successful national seminar at Lucknow. Large number of participants they have attended. The main impetus of this type of activity is to indulge and encourage our scholars to be in touch with the academic staff from different institutions, from different countries, so that the concept is to have an academy which confine not only to the members, but it is open to all the scholars. And I on the behalf of Academy again request all the scholars to be in touch with the website of ANRCM. Try to become member. You will have a very, I will say, the best experience and guidance from all of us. And again, the all registered attendees, they will be getting the certificates in due course of time. On behalf of Academy, again, I'm highly thankful to all the 4 eminent speakers. See, the navigation is from Australia, Dr. Srivastava to India, Dr. Srivastava from Adelaide to Uttar Pradesh, India. The success goes to all of you. I'm highly thankful to the Academy that they had given me the opportunity to be part of this webinar. And I wish you all the best. And we look upon each other as a source of strength. And we will be taking the key points from today's webinar, whatever speakers they had discussed with us. We will be inculcating all this into our studies, into our research programs. And that is the main motto, that every day is a World Environment Day. It is not a one-day celebration. Every day your activity should be like that. Your carbon footprint should be less. You should do all those activities which in turn can reduce the carbon footprint. Again, I'm thankful to all of you, and try to be in touch with the ANRCM through website, through email. Thank you very much. Have a nice day, and thanks to all scholars, attendees, and eminent experts. Thank you. Dr. Kohli, shall we?
Yeah, we can end this webinar. Just before ending, I have just 1 or 2 announcements. The e-certificates of the quiz winners will be given in a few days. Similarly, the certificates for all the registered attendees will be dispatched through email. But just give us some time, maybe like 1 or 2 weeks to complete this process, because there are a large number of participants. And nothing more. I would like to thank one and all for participating in today's webinar. It has been an immensely beneficial learning experience. On behalf of ANRCM and on my own behalf, I wish to thank all involved. Dr. Arya has already thanked them, but maybe we could have missed someone. So everybody, thank you, and hope we all meet again sometimes again in another webinar. Thank you.
Thank you, Jai Hind, sir. Thank you.
Jai Hind.